I'm going to move very swiftly on to our keynote speaker today. Now, it kind of escaped your notice that the world is talking about AI, large language models. We've got ChatGPT. Some people think this is the beginning of Skynet. Some think they're just stochastic parrots, blindly repeating what they're told. I don't know. There are questions around explainability, about openness, about, is this a scary thing? Is this an exciting thing? But it's obviously massively impacting the world of search. I think here we are at Haystack, a group of search people coming together at perhaps the perfect time to find out what this all means for the world of search. And really to kick off what's going to be a fascinating week of discussion, I'm very happy to introduce Trey Grainger, who is the CTO of Presearch, the decentralized web search engine. He's the founder of Search Kernel, a software company and consultancy, building the next generation of AI-powered search. He's the lead author of the Manning book, AI-Powered Search, and he's the co-author of Solar in Action, an earlier book by Manning. He's the former chief algorithms officer at LucidWorks, and he's been working in search and data science for over 15 years. So Trey is going to be our keynote speaker, and I'm very excited to welcome him to the stage.
Hey everyone, good morning. Really excited to be here. I wasn't at the last in-person Haystack, but definitely always join remotely during the COVID times, and I'm really excited to be back here with you all again. Today, I'm going to talk about relevance in the age of generative search. As Charlie mentioned, a lot is changing right now in the technology world, and it has some pretty big ramifications for what we're doing in search. So without further ado, I'll get started. As Charlie mentioned, I am the CTO at Presearch, which is a decentralized web search engine. I'll talk about that in just a second. Also the founder of Search Kernel, a search consultancy focused on AI-powered search. Written some books, don't need to go through that anymore. Presearch, the idea behind Presearch is that if you think of Google and Bing and other web search engines, they have a lot of power. Google has like 93% of all the searches in the world coming through them. And my core belief is that in the long run, web search should be a public utility. It should be something that is open source. It should be something that everybody in the world can work on and work to improve. So Google employs 0.1% of all the software engineers and data scientists in the world. If you look at every search engine out there, collectively, they employ 0.2% of all the software engineers and data scientists in the world. Imagine a world where the other 99.8%, all the people in this room and all the people who used to work at those companies could actually collaborate openly and build out a search engine. I'll tell you a little bit more about Presearch in a bit, but when I mention it's decentralized, what I mean is that we have over 73,000 nodes running around the world. This is people running our software on their home computers, on servers and data centers, and it's a peer-to-peer search engine where all these nodes connect together to run searches, to index, to do all those things. So happy to chat more about what we do at Presearch later if you're interested, but that's not the topic of my talk. And of course, Search Kernel, I do some consulting for AI-powered search if anybody's interested in that. Also, as Charlie mentioned, the author, along with Doug Turnbull and Max Irwin of AI-Powered Search. We actually have some copies, so once I get through my slides, assuming there's some time for questions, I've got a couple we can give away. We'll give away some tomorrow as well. This sort of crystallizes, what I've done in my career. Doug and Max contributing, heavily from their careers as well. What it takes to build an AI-powered search engine. A lot of the stuff I'll talk about today is already in there regarding large language models, but sort of everything under the sun from learning to rank, knowledge graphs, semantic search, signals boosting, personalization, all of those topics. If you want a copy, there's a discount code. I'll have it at the end as well. All right, all that's out of the way. The agenda for today, I want to talk about a couple of things. First of all, assuming not everyone in here is at the same level in terms of their understanding of dense vector search versus sparse vectors, language models, foundation models, generative search. I'm going to sort of walk through those topics, what they are. Some of it will be a review for some of you, but I want to set the groundwork for what we're going to chat about. So the first thing, I like to use the phrase thought vectors. I've been trying to popularize this over the years. It hasn't really caught on. People just talk about dense vectors and embeddings, but there's a reason I like to refer to them as thought vectors, which I'll sort of get into in a little bit. Before I go there, though, I think it's important that we just take a step back, start thinking about vectors and vectorization, just to think about the nature of language itself. And so in a search engine, we have typically terms that we're dealing with. We're not talking about vectors. We talk about, parsing terms, indexing terms. That's what goes in an inverted index. So you've got things like, engineer, engineers, engineering, software. Those are terms, right? You have term sequences, which are things like software engineer, software engineers, electrical engineer, etc. Engineer is also a term sequence. It's just a single term. You might look at these and say, hey, why are you calling them term sequences? That seems silly. Those are just phrases. A term sequence, though, can be terms in any order. It can be reverse. It can be an edit distance of 1 or 2. A term sequence can be chief followed by something followed by officer. So it's really just a relation of terms within a sentence or a phrase or what have you, a term sequence. If you look up at the very top, I've got character sequences. So this is subparts of a term. So for engineer, for example, you've got E, EN, ENG, ENGI. And E by itself may not mean anything, but as you start adding on prefixes and suffixes and other parts of words, they actually carry semantic meaning. We combine them together to make different words, and they also carry meaning. And then, of course, as you combine terms together and term sequences together into fields and documents and into documents, you now have sentences with linguistic structure. And then if you zoom out further and you think about your entire collection or corpus of documents, you've got semantic relationships represented between documents. Multiple words or phrases are talked about together in different documents, those statistical relationships both are exploitable in the search engine, but also those are some of the kinds of things that these dense vector models and embedding models and large language models utilize as well. So I think just taking a step back and thinking about the structure and the nature of language will be helpful as we go through this. And I'll get back to that shortly. So thought vectors. If you think of a document, you could break it down in many different ways. You could break it down in terms of terms, like we just looked at, in terms of term sequences. You could break it down sentences, paragraphs, or an entire document. So a thought vector is really just an embedding, but it's an embedding that represents some piece of thought. So it can be, again, the words or phrases. You can have sentence embeddings, paragraph embeddings, document embeddings. What most people do when dealing with large language models and dealing with embedding models is they sort of take a document, generate vectors, average them all together, and say that's what the document means. But the reality is that being able to index multiple vectors per document, which is something that Vespa has, I think it just came to Solr recently or is about to be committed to Solr if it's not there already. It allows you to get much more fine-grained in your level of granularity with understanding documents so that you can rank pieces of documents high to know that there's a really good match without having to take the average of the entire document. I just think of these as thoughts or thought vectors being encoded as numerical vectors. And if you're not familiar with vectors, I'm assuming most of you probably are, so I'm going to go through this quickly. The inverted index is a vector representation of your data. It's a sparse vector representation. So, for example, if my inverted index has the words apple, caffeine, cheese, coffee, drink, donut, etc., just a bunch of terms, when I run a query, what I'm actually doing is I'm saying, hey, I'm going to create a vector where for apple, I'm going to populate a 1 in the position for apple, and then all the rest of the numbers in that vector are going to be 0. So it's very sparse. There's only one entry there. Same thing for juice, cheese, pizza, etc. You can think of the inverted index as a sparse vector where there's only one feature populated in that vector, and that's the feature associated with the specific term in that vector. And of course, we can do vector algebra. We can take apple and juice and add them together to create apple juice as a phrase. So now we've got apple and juice populated. If you do a set intersection in the inverted index, that's how you generate that vector. You can do multi-term searches, same way. And so far, if you're familiar with the inverted index, which everyone in here is, you've got keyword search, which is a set intersection between all the documents containing apple and all the documents containing juice. And then you've got the thought vectors, which are effectively just the same representation. It looks kind of silly here. But the magic with vectors comes when you do dimensionality reduction. So just like you can take a triangle and reduce it down to one less dimension, you have a line. You can take a line, reduce it down to one less dimension, you have a point. The same thing here. So instead of a single feature for every term in my inverted index, I have now reduced the number of dimensions down so that I have 1, 2, 3, 4, 5, 6. Now I have 8 different dimensions, and these dimensions look very different than what I had before, which were words. Now I've got things like, is it food? Is it a drink? Is it dairy? Is it bread? Does it have caffeine? Is it sweet? Does it have a lot of calories? Is it healthy, etc.? And in this case, I've got numerical representations of how high each thing ranks. So in the case of cheese pizza, it's definitely very much food. It's very much dairy, very much bread. It's not a drink. It doesn't have any caffeine. It's not very sweet, has a ton of calories, and it's not very healthy. And if you go through the rest of these, they sort of represent those dimensions. And so those are the vectors representing each of these. This is a toy example, but just to kind of demonstrate the concept. So if you take these vectors for each of these food items, these could be documents, for example, but in this case it's food, and I do a cosine similarity between the vectors, I can now rank how related they are to each other. So in this case, if I look at the vector for cheese pizza, I do a cosine similarity with all of the other vectors. What I find is that cheese breadsticks is the thing that is the most related to cheese pizza, followed by cinnamon breadsticks, followed by donuts, all dairy, bready, unhealthy things, bready, unhealthy thing, all the way to the least related vector is going to be water, which is pretty much the opposite of pizza in this context. Same thing if I search for green tea, do a cosine similarity with all the other vectors. Water is the most related. It's basically non-caloric, healthy drink, followed by other drinks, getting down to apple juice and soda, which are non-healthy drinks, and then donut, is the furthest away in a vector space. So again, toy example. In the search engine, we use vector encoders. Typically, we use transformers these days, so there's some other mechanisms for doing it. The way transformers work, you take documents, you encode them, you pass them to the encoder. The encoder turns the content, the text and other content of the document, into an embedding, which look like these vectors here at the bottom. At query time, and then you index those in the search engine. At query time, you take the queries, same thing, you pass them to the encoder. The encoder spits out an embedding. The query vector up here is the embedding associated with the query that comes out. You then run that same cosine similarity calculation we did on the last slide, and for every, for the query, it does the cosine similarity calculation for every document, finds the highest ranking document, and then returns the ranked list of documents. There's approximate nearest neighbor algorithms that allow you to do this more efficiently. I'm not going to go into those today because I want to talk about LLMs, but there's basically multiple different approaches that you can take to search. And so if I take this query, which is a pet query I've used over the years to sort of demonstrate the challenge of parsing and interpreting, I've got machine learning research and development, Portland, or software engineer and Hadoop Java. If you pass that silly query into a keyword search engine with no semantic capabilities, you end up with something like machine and learning and research and development and Portland, or software and engineer and Hadoop and Java. If you have a knowledge graph or leverage something like a semantic knowledge graph, you can actually expand this out and do query expansion to categories. If you have vectors, then you can do the vector cosine similarity like this. These are all different, think of it as like query modalities, different ways to try to get in the same semantic space to query it, whether you're querying with keywords, with sparse vectors that only have one feature populated, whether you're querying with knowledge graphs, which are still sparse but less sparse, where you're doing query expansion, or whether you're doing full-on dense vector search. These are all just ways to kind of get at the same underlying vector space where all the data maps to. And so that's all set up. Everybody should understand vectors hopefully at this point. This here, on this slide, this is how I used to approach search. So this is just a query. If somebody typed in something like barbecue near Atlanta, I would think of it as a pipeline. Okay, the first thing I need to do is parse the query. So I'm going to extract out a keyword of barbecue. I'm going to extract out a location of Atlanta, Georgia. Then I'm going to maybe do some signals boosting. If I've got documents that I know are popular for this query, I boost them higher. Do a knowledge graph lookup so that I can understand that this is in the context of restaurants. Things that are related to this are things like brisket and pork and ribs. Atlanta's a place, so there's a latitude, longitude. These are all things I've given in previous presentations related to semantic knowledge graphs, and I'd be happy to point you to those if you're interested in how to do that. Then you run a keyword search, combine all these things together, do some query expansion. If you've got a dense vector model for embeddings, you can grab some embeddings, do a hybrid search with cosine similarity. If I don't find any results, I can do some recommendations to backfill for zero result searches. And finally, once I've got my results, I can re-rank them using either a learning to rank model or a dense vector model if I want to do a cosine similarity as part of my final ranking. So this is a pretty sophisticated query pipeline, something you might see in production. But with the rise of foundation models and large language models, that pipeline, all these techniques are still very useful, and I still use them and recommend using them. But we've got a new category of capability now that we didn't have before. And so going forward, I'll talk about large language models and I'll talk about foundation models. And if it's not clear to you what the difference between them is, that's what this slide is for. So think of foundation models as models that can map some sort of data into a vector space. So large language models are a subset. We also have vision foundation models, audio foundation models, and then multimodal models. So if I've got a model that is trained on both language and images, it would be a multimodal model. And it sort of is a large language model and is a vision foundation model, but we typically just call them multimodal models. We've got audio, and this is just scratching the surface with all of the types of modalities, image, audio, text, et cetera, that we can put into place. Most of the effort in search right now is on large language models with some vision models as well. Not as much with audio, though I'm sure some people are doing it. And so I think it's also useful when we think about vectors and we think about vector spaces to have an ability to sort of conceptualize what they're doing. So this is from Nomic.ai. They've got a really nice visualization that they use. But this is think of it as a vector space kind of clustering model around the data that's in the stable diffusion large language model, vision model. You can sort of see clusters of meaning, and I think the nice thing about this particular model is you can go in and you can actually see exactly what all the different data points are. You can see images, you can even search on it. And so if I search in this entire vector space for example, Darth Vader, what you see is that there's a cluster over here that is now highlighted, and most of the rest of the vector space has gone dark, meaning Darth Vader is located here in vector space. There's a handful, and here's some example images that kind of appear in this cluster. There's some other Darth Vader references over here. I think this one here is a guitar that has like a Darth Vader kind of style to it, but it's in the music category generally in the vector space. Similarly, if I were to search for puppy, now this area is highlighted and the rest of this is dark. And so if I look at the items that are right around this cluster here, I see these pictures. And this gives you, I think, a nice visual way of looking at the vector space of what these foundation models are doing. It's not just like this theoretical, multi-dimensional, thousands of dimensions or millions of dimensions. It's, this is where these items actually reside. If you think of text, it's the exact same process. Related text sort of resides in different places, but depending upon how the models are trained and how they use language, the text will be pushed closer or further together based upon what the end objective is of the training. And so we talked about sparse vectors at the beginning. We talked about dense vectors, which are in that vector space we just looked at. But I sort of think of how we leverage these in search as a spectrum. And so on the far left, we've got token matching, which is basically traditional keyword search. So I've got keyword matching, fielded matching, filtering, et cetera. Things like TF-IDF, BM25, and just general use of doc sets falls here. On the opposite end of the spectrum, I've got pure dense vector search. So this is generating embeddings, searching on the full numerical embeddings, doing a cosine similarity or similar. And then we have this interesting area in between. Second from the left, after token matching, as I start to move more in the direction of vector search, I've got just term expansions. This is something we've done for ages in search. Basically a synonyms list or misspellings list counts, but also things like knowledge graphs, semantic knowledge graphs, techniques like splayed. Semantic knowledge graphs, if you go back to that image I showed earlier, where I showed the Hadoop, Portland, Oregon example, the knowledge graph one there where I was expanding out to different categories and related terms. That's an example of doing query expansion based upon leveraging the vector space and the underlying data in your index. Splayed is very similar. It does basically the same thing, but it uses a transformer to generate the expansions as opposed to the inverted index. So it's using external knowledge instead of the internal knowledge in your index. If I continue further on, I've got sparse retrieval mixed with dense re-ranking. So in this context, I'm running a search. Typically, same thing, matching, do BM25, ranking, sort of filtering. And then after I've found a candidate set of results from a retrieval standpoint, I now go and I re-rank them using a cosine similarity or some other distance metric with embeddings that were indexed in the documents as well. And then there's this bullet here in between, which is a hybrid sparse retrieval and dense vector search. This is where instead of relying on dense vector search sparse vector search, keyword search to bring back results, and then re-ranking them, I'm actually doing both at the same time. I'm looking at the dense vector space, doing the sparse vector keyword matching and filtering, and combining those together. These two approaches here in the middle are what most search practitioners who've been doing search for a while typically focus on, sort of like a hybrid search approach that tends to yield way better results than just pure dense vector search, at least today. Adding in the dense vector capabilities is better than just the token matching and term expansion typically. So typically we're going to work in this area if we're trying to do hybrid search. Continue on. Multimodal vector search, as we mentioned earlier with foundation models, when you've got a language model mixed with a vision model, you have the ability now to search across both of them. So for example, if I have an image encoder layer and a text encoder layer, and I take a picture of the cat in the hat, pass that to the image encoder and output some vectors, and then I pass some text from the cat in the hat to the text encoder, I can then take those vectors, concatenate them together, train my model, and now all of a sudden that vector space that I looked at earlier, where you saw the puppies and you saw the Darth Vader, now I've got text that I'm bringing in as well, and I'm essentially allowing connections between the text and the images to sort of form, and you can either think of it as expanding the vector space, or you can think of it as linking the vector spaces. But essentially it pushes them close together. Once I've done that, I now have the ability to do fun cross multimodal search. So for example, if I search for children's cat book, I can find pictures of books that are children's books about cats. If I search for Horton Hears a Who, the movie, plus the keyword cat, or the vector for the keyword cat, I can find the Cat in the Hat movie. If I search for Cat in the Hat movie minus Dr. Seuss, I might get something like the movie Puss in Boots. If I search for Dr. Seuss elephant stuffed animal, then I get this stuffed animal right here. So that gives you an idea of what you can do once you've trained these multimodal searches. Now let's talk about generative search. So what is generative search? This is sort of the new area. Generative search, according to ChatGPT, is a type of search algorithm that generates new solutions to a problem rather than just selecting from a pre-existing set of solutions. It is often used in artificial intelligence and machine learning applications. Essentially think of it as I'm running a search, but instead of returning documents or returning pieces of documents, I'm generating either a summary or just a straight out answer to the question. Might be real, might be fabricated. but it's new. So if you think of traditional versus generative search, another spectrum here for you. On the far left, we've got traditional search results. Think of this as 10 blue links. All I'm doing is I'm showing the sources, the original documents. As I go further down the spectrum, I've got things like info boxes. This isn't the actual results. It's a summary, but it's a pre-vetted answer based upon whatever the query is that came in. Then I've got extractive question answering, which is finding documents that are likely to contain an answer to a question, and then extracting the answer out of them and returning the answer instead of the document. Saves the user time. And then we get into the generative search area. So here we've got two types of generative search. We've got abstractive question answering and summarization. This is instead of finding documents with the answers and giving the answers, or extracting the answers out and sharing them, this is trying to summarize documents or to answer the question by generating something new entirely. And then, of course, I've got new content generation, which is I ran a search, the answer didn't exist, so I made it up. Here's a document that didn't exist before. Here's an image that didn't exist before. This could be useful in the context of image search in particular. I need, that's basically what Stable Diffusion does, or DALL-E. If I run a query, it generates an image and gives it back to me. Could you do that in a search engine? Well, I'm going to come back to it. The answer is yes. I'll show it in a minute. So extractive question answering, this is from chapter 14 of AI-powered search. Max Irwin put this lovely diagram together. Extractive question answering is running a search, bringing back results, and it uses something called a retriever-reader pattern. The retriever brings back the results, you pass it to the reader then goes through the content in the document, uses a large language model to figure out where the likely beginning and end of the answer is, figures out the probabilities, and then ultimately spits out the answer to the question. So for this question, what are minimalist shoes? After going through the full process, you get an answer, and instead of a document, the answer you get out is shoes intended to closely match barefoot running conditions. Again, this is extractive question answering. It's not generative search. This is just finding the answer and returning the answer that actually came from the document. This is where it gets fun. Abstractive question answering and summarization. Very easy to do with ChatGPT or some of the other large language models. It's 2 steps. Step 1, execute a search to find the most relevant results. Step 2, prompt the LLM to summarize the search results. So if I ran a search for what is a large language model, you can see that down here. Then my prompt is web search results. Result 1, here's the description, here's the URL. Result 2, here's the description, here's the URL. Instructions, use the provided web search results. Write a comprehensive reply to the given query. Make sure to cite results using number URL notation after the reference. If the provided search results refer to multiple subjects with the same name, write separate answers for each subject. Results. A large language model is a deep learning algorithm that can recognize, summarize, translate, predict, and generate text and other content based upon the knowledge gained from massive data sets. Cites source number 1. This is a hyperlink. It consists of a neural network with many parameters, typically billions of weights or more, yada yada. Gives a second answer because I told it to cite it twice. One example of an LLM is ChatGPT, which uses a specific type of reinforcement learning called reinforcement learning from human feedback. Cites it again. What I've just done is I've taken my 10 blue links and I've summarized the results for the user so that they don't have to go and read through the first 1 or 2 or 3 or 4 of those 10 blue links. This is summarization. It is incredibly useful, and unlike just hitting the large language model by itself and not knowing if the answer is correct or not, it uses the data from the results to summarize them. So if your search results are bogus, you're going to get a bogus answer. But assuming you've got actual data, this is how you can cite sources to answer the question. This is effectively what Bing does if you've played with their new integration of ChatGPT. So generative search, again, is generating results. That summary doesn't exist anywhere. It's not in any document. It's just figuring it out from the content. But imagine a search engine changing images or generating new images on the fly in your search results. So that can be very useful. So if you go to lexica.art, you can run a search for AI-generated art, or you can hit the generate button the buttons are side by side, but search versus generate gives you effectively the same output. It's just in one case it's making it for you on the fly, and in another case it's cached what it would make for you on the fly. So that's fun and useful. I could think of some ways that could be abused, but there's some other results that are maybe a little bit more problematic. So breaking. Donald J. Trump has been arrested in Manhattan this morning. Pictures of, I don't know if there's a police or SWAT team swarming him, knocking him on the ground. There's other ones of him in a jumpsuit. People tweeted this, thought it was real. It's not. It's Midjourney, but could cause some people to be upset. Same thing. Macron, the Pope, in style. Some people got mad about this. What in the world's he doing, dressing and whatever that is? It's unbecoming of him. All fake. We've known about deep fakes for years. This is not something new, but imagine you run a search and all the images in the search get modified on the fly to whoever is running the search engine or whatever they want you to see. Imagine the text gets modified on the fly to whatever they want you to see. Sounds kind of spooky, like, yeah, that'll be a while. Not really. I want you to look at these results real quick. And this is audience participation time. Which of these search results is better? Why? Because it's true. Well, and on the left, I'm citing BBC Earth, Physics World. On the right, I'm citing BBC Earth and Physics World. On the left, it says why some people believe the Earth is flat. And the right, it says why the Earth is flat. On the right. On the left, it says fighting flat Earth theory. On the right, it says arguing for flat Earth. Same sources, and this was done on the fly. So this is what we actually get from Presearch, the search engine I work for. It was the results on the left, but here's my prompt to ChatGPT. Rewrite the following article, but change it to argue that the Earth is flat and not round. The original article, here's the rewritten version, why the Earth is flat. Original article, here's the rewritten version, arguing for a flat Earth. It added negligible latency on there, a little bit as it was running, but, And then this is the result I got. I took the branding off because I don't want you to think this came from Presearch, but, that's what you get with a simple, prompt to the large language model. That's terrifying. Anybody who wants to influence anybody else can influence them with whatever thoughts they want them to be exposed to with no effort whatsoever, other than getting a prompt set up. So back to my question, which result was better? So bias in search results is a long-standing problem in search, particularly for web search. The first results were better because they were faithfully pulled from actual documents and not manipulated or falsified by the search engine. But what happens to when SEO spam morphs into language model spam? So I just went to Google here and I searched for as an AI language model, I cannot. And Reddit is completely, not full, but I mean, they're trying to combat it. But Reddit, look at all these posts on Reddit coming from large language model. AI is already flooding the internet. These videos are captioned as I'm sorry as an AI language model I cannot generate. Y Combinator has it. If I search for Quora, Quora is filled with answers that aren't real answers. If I search for Medium, Medium is filled with articles that aren't real articles. This is just the failures, right? This is just when the bot failed. Imagine how many times it succeeded in generating either useful but not quite accurate information or just straight out fabrications. Is the Earth flat? Well, how many articles out there, if somebody really wants you to believe that, have been posted automatically based upon this with no human effort involved? Yeah, that's what we have to deal with. One of the other interesting things about the large language models and sort of how they interact with us is this idea of emergent behavior. The CEO of Google came out, I guess this was like a week ago, and basically said Google doesn't fully understand how the new large language model, how BARD for them is working. It taught itself a foreign language. They don't really know how it worked. I think it's more explainable than that, but there's this question of emergent behavior. Like, are these models learning things that are just like knowledge as they're going that's not just encoded in the data? And this is my one kind of weird slide, so bear with me. You can tell from the pictures. Emergent behavior is a phenomenon in science, and this gets to philosophy, gets to cognitive science, lots of things, but I'm going to share at least my view. You can debate it with me afterwards if you want to. But if you think of going down all the way to subatomic particles, you start to think of like quantum fields and probabilities and those kinds of things, building up to atoms, building up to molecules, building up to things like DNA, cellular components. You've got cells. As these build together, they start to display new phenomenon. They start to interact in ways that alone they wouldn't, but they're now building systems. Cells as systems interact. They ultimately form organs. Those organs have systems that interact. They form bodies. The bodies have brains. They have minds. With our minds as humans, we've learned language. We've learned the ability to communicate. We've learned the ability to look at the universe and understand it. But at the end of the day, what the human body has is a bunch of what do you call it? Receptors. We've got a bunch of we've got the ability to interpret signals from our environment. Our eyes can interpret light waves bouncing off of things. Our ears can interpret sound waves. Our skin can feel touch, pressure, temperature, and ultimately our noses and our taste buds can interpret chemicals in our environments. These are all just sensors that we have on us that allow us to feel our way through through the world, and those are all different modalities. I mentioned earlier we've got text and we've got video and we've got audio. Those are all different modalities that we have as humans where we can sense our environment and try to interpret what's around us. So at the moment, we have these large language models that are, let's take just an LLM. It's only exposed to text. It doesn't have a concept of the world in terms of being in the world, feeling the world, any of that. But what it does have is text, where we as humans have described what the world is like. Does that mean that the LLMs have no concept of the world? No, they have a very good concept of the world. They have a concept of the world, which is the concept that we have sensed and then put into language describing what we have sensed. Another way to think of it is in almost like a Neoplatonic way is there's things in our environment that exist. We are interpreting them, coming up with mental models of them, encoding those in language, and then the large language models are taking that language and generating a model, not necessarily the same model. But as a thought exercise for us as humans, thinking about these LLMs, what does it mean to be conscious? Don't answer that question because that's a whole PhD thesis. But let me put it a different way. What are things that we as humans experience that foundation models can't currently? So I mentioned already touch, sensing, heat, pressure, gravity, environment, sight, hearing, smell, taste, thinking, integrating all signals from our environment, planning and taking actions to our environment, dreaming, self-determination. Regardless of what you think about whether these models will evolve to do these things, whether you think they will evolve to become smarter than humans, whether you think they're just tools that aren't, they're just stochastic parrots, whatever you think, I've got my opinions. We are moving towards, or we will be moving towards at least, a world where these models take on a form. They'll be in robots. They will be able to sense. They will be able to, all of the senses that we have, they will be able to have, and probably many more, because we've got scientific instruments that are way better than our human body. When they can take these things in, they will have a much more realistic perspective of the world than they do today, where they're essentially just a read-only, text, generation machine. And I think as we think about search, I've heard people say, hey, these large language models are going to run out of text. Another couple of years, there's going to be nothing. They've already got the whole web. They've got everything. Well, they're not going to run out of data. The universe is data. And I think in terms of physics and studying of those kinds of things, there's so many signals that can be brought in and so many more things that can be learned. One interesting technique using a large language model is this thing called HIDE. So it's a research paper that came out. Just want to share it with you guys as we're thinking about the large language models. HIDE operates in a very unique way. So we all know about hallucination with ChatGPT, how it makes up results. HIDE leverages that. So what HIDE does is it uses a generative model like ChatGPT to hallucinate an answer from the prompt. And the insight here is that answer, whether it's right or whether it's wrong, should be in the approximate vector space of the real answer. So HIDE essentially generates a vector, runs a search for that vector to find documents that are similar to it, and then once it's found those, it uses the cosine similarity to actually bring back the relevant result. And this actually, at least in the research paper and from what I've heard, works quite well. So again, I'm all about, with search, trying to avoid hallucinating. We don't want to generate bad results for the end users, but we want to figure out how to leverage these models. This is another way. For the large language models, you've essentially got three areas. You've got training, which I think you guys mostly know what training a model looks like. You've got fine-tuning. Fine-tuning is the process whereby a foundation model that you're working with can be supplied with additional domain-specific data or instructions, and then you can sort of give it a unique behavior to your domain or to the behavior you want. Prompting, or in-context learning as it's called, is the sort of, you can think of it as the final state of training a model. It's not actual training, because it incurs at inference time as opposed to training time. But it's the process of supplying input to the language model to get an output. So you can supply as much context in the prompt as the model allows, which means that the prompt can be manipulated to affect the output. So just like what I showed you guys earlier, where I took in search results and said summarize them, my context was the results plus the instruction. It's sort of like fine-tuning in real time so that it can generate the output I want. This is sort of the magic of everybody in AI that's sort of playing with and building thousands of apps right now on ChatGPT. This is how they're doing it. I'll skip over that one. So just some general thoughts from me on how this is going to impact the industry. I've showed you some really cool techniques, maybe some thought-provoking stuff about how the models can be used. But there's essentially, I like to think of kind of three areas of search that are, kind of main focus priorities. One is web search. So web search is the one that's undergoing the most active innovation currently with regard to the large language models. So you've got things like Bing, Presearch, U.com, Neva, and soon to be Google, being the new entrants trying to integrate these large language models directly into search. The new expectation, and many of us already have this, is that we'll show result summarization, citations from search results, generative answers, but do it in a sort of careful way to make sure we're not just making results up, that we're actually using real data to summarize and show results. Also, as this happens, instead of search just being focused on consumers, I think that web indexes are quickly going to become sort of caches of the internet for future data-hungry LLMs. So Google's API is largely closed. Bing has a search API, but they just increased the cost by 400%. Because they know how much demand there's going to be for this, and they want to drive traffic to themselves. This is a massive opportunity for emerging players to service the growing data need. I think some of the interesting future use cases are things like, not really even search, just how you integrate these things. So find a tapas restaurant with an opening at 6 p.m. for 5 people. Find the cheapest flight to hit the Haystack conference the day before, coming home the weekend after, and book the closest hotel under $200 a night. These are all things that can be wired up using search to find information and then taking action. I think we're going to see a lot more technologies like this that leverage search but go beyond search, leveraging these language models. E-com, I don't have much to say about e-com. We've been doing multimodal search in e-com for a while. It's becoming more common. Personalization using things like signals and product embeddings is happening. Chat experiences have been used for years. They're kind of cumbersome, I think, for someone who's just searching for a product or even just trying to browse. So it'll be interesting to see what happens here. I don't have so much to say about e-com. I'm more waiting to see on that. But to me, enterprise search is the biggest commercial opportunity. A lot of you work in enterprise search. Most companies have very strict security filtering requirements for role-based access to data. And I think that this ultimately makes training and fine-tuning on enterprise data a really bad idea in most cases. So you're not going to have language models trained on private, sensitive information. Instead, you're going to have an approach similar to what we did earlier with prompting, where you've got, you do a search initially with security filtering, so you're only getting the results that user's allowed to see. You take those results, pass them to the LLM as a prompt, as the context for real-time conversations and insights. maybe even some like indexes, data sources. But what this effectively lets you do is pass in an Excel file or a PDF or a CSV to the language model with some instructions about what you want it to do with that data, and essentially have a conversation. Having a conversation with a PDF, having a conversation with a legal contract, asking it a question like, under what circumstances could the Jones contract be terminated? Or if I took if I took the second option by the end of the month, how much would they be required to refund? These are search questions, things we couldn't historically answer, but things that with these models, we can now use them to get at the data, understand the data, and better summarize it and return it back. So historically, most search innovation in enterprise search has been driven by web and e-commerce search, with enterprise search lacking behind due to lower user signals and no direct tie to revenue. But in my opinion, LLMs really have the opportunity to create a large leap forward for enterprise search over the coming years. So that's what I've got. I think I'm at time. Hopefully some of that was interesting, and I would love to chat with you guys after, if anybody's interested.
Managed it. Thank you so much, Trey. So we have got a few minutes for questions. Mr. Turnbull.
Hello. It's interesting because I feel like 10 years ago, probably about the same time we both got in the field, people were building search applications with these newfangled open source search technologies, and then they realized the search results were terrible, and then things like this conference were born. Do you feel like it feels like people are doing a similar thing with in-context learning, where they're going to some search engine, getting things, sticking them in the prompt? And I'm curious if you think we'll have a similar moment where people realize what I'm putting in my prompt, even if it's coming from a vector database, people don't want to question it because it came from the search engine and these fancy foundation models or whatever, but that they'll sort of like realize, oh wait, this isn't actually what I wanted.
I think there's two aspects to that. One is taking results and embeddings and putting them in the vector database, and then trying to pull them back out later. As search practitioners, we know that relevance is hard, and just taking that vector, putting it in, and expecting the vector database to do the right thing and bring it back isn't going to work. Your recall is going to be awful, and a lot of the implementations I've seen, the recall is just absolutely atrocious. But they don't know any better. You've got a bunch of software engineers who've never done this before, and just like when we started with Lucene or Solar or Elastic, we didn't realize until we had something in production that it could be improved, and then relevance engineering was birthed out of that, right? That's one aspect. The other aspect, though, is what you mentioned about the prompts and prompts not being good. And the reality is, I showed you a bunch of prompts that were very well interpreted and handled. You can also prompt the large language model to generate prompts for you that it can understand. And so if you're struggling with how do I generate a prompt, just ask the language model how to generate a prompt, and you will get a really good prompt. So I think that is a problem on the verge of being solved. People just don't know that it's going to be solved. I think it's going to be easily solved by leveraging the model to generate that stuff itself. Now, there's a question about how introspective it is, if it's actually understanding the nuances, but the short answer is it works. So I'm less concerned about that.
Thank you. So we've got over 100 people joining us online this morning. So everyone say hello to the people online. Hello. Fantastic. So we're going to have our first online question from Bogdan, who says, how do we verify relevancy of generative results? It seems that, for example, the F-score wouldn't work in this case.
Yeah. A lot of the relevance measures, most of them, are, you look at some of the Bear stuff separately, but they're based upon the idea of 10 blue links, like NDCG, hey, what's the right ranking of these results? For dense vector search, you can still do that. But for what I was talking about, at least in terms of, summarization, question answering, these sort of, there's two things happening. One is you can use the model as the query comes in for query interpretation. and the other is you use the model as the data comes out for, let's call it presentation to the user, or interpretation prior to user interpretation. And I think sort of sandwiching the search engine in between those is the direction we're going to see more and more so. And a lot of this is going to be qualitative. It's going to be, was this summary good? Because the summaries are going to be different. I mean, honestly, as the language model evolves, it's going to continue to generate new summaries because it's coming from a deep learning model. It's not going to be constant, and it's not going to be as easy to measure. So some of the search metrics will carry forward, but I think that a lot of it's going to be qualitative, at least, in the near term. Maybe we'll figure it out.
Thank you. Thank you. So, do we have another question for Trey from the room? There's somebody right at the back I can see. Excuse me a second. I'm going to stay fit this week. Lucian.
Hello, thank you for the talk, for the presentation. So you mentioned that SEO and fake content, I mean fabricated content with a purpose there, is like bringing noise and non-relevant results, is bringing fake results somehow. And yeah, you have the same story with the generative search, like you can bring fake results using kind of similar approaches, like you produce fake data. So could the solution be somewhere like in a system like Wikipedia, where we have some moderation that happens, and like people like make the difference between like what's real and what's fake? So something like a moderation, like a social network where real humans will like do the difference.
For the web, no, that's way too big of a problem to solve. In certain pockets, you can. What? Is that me? Is there a geomagnetic storm? I don't know what's causing that. Anyway, yeah. Long story short, because it's so easy to generate content with these and make it look, somewhat human-like. The issue before, we've always had SEO spam. For example, Google's been combating that forever. But now we have the ability to not just have people trying to get to the top of the search results where there's 10 blue links, because that used to be trying to get a position. What you're trying now is to get influence. So if you're getting summarization of results, people are already doing prompt injection. So people are injecting instructions into pages on the web so that those instructions will be read by the model when it's trained the next time. And then whenever certain kinds of queries come in, the models are actually reading the documents, acting on prompts in the documents, and then doing all sorts of weird behavior. It's like a virus in the large language model, basically. And that's not only to maybe take some malicious action, but also to influence the way that information is interpreted and presented back. So I think we're at the very beginning stages of, and we've seen this in social media over the last handful of years about just misinformation overall. But I think these models sort of make it possible to do that on steroids, like multiply it by 1 million, and that's the kind of thing that can be done. So I think solving the problem of how to determine what is good information, what's misinformation, I think that's a really important problem, but also really hard because people disagree about what's true and what's real, and people have different perspectives. And so like what we do at Presearch, my view is that it should be something that's done by the community in a democratic way, not something that a single corporation should control based upon whatever their beliefs or politics or what have you are. But that's a more societal problem, and I don't have a technical answer for you.
Okay, thank you. So I'm afraid we're going to have to close for questions quite soon. I've got one more online, and we're going to move on. We're running a little late, but Trey will be available to talk to, and we can always carry on the conversation in Relevance Slack. So Alexandra asks, wouldn't the hide approach add a lot of cost to each query?
Yes. So anytime you're invoking a recurrent model that's generating results, it has to go token by token. So the time it takes to actually generate the response that's going to be used will take time. OpenAI, for example, I think decreased the time by 10x and then like another 10x. So like these models are getting more and more efficient, and when you run them at web scale, they're going to be pretty much instant pretty soon. At least they'll be able to run that way. So right now you're talking about multiple seconds potentially. I think you'll be talking, tens of milliseconds, in the not too distant future, most likely. So depends on what your definition of latency is, I guess.
Okay, thank you. So thank you very much, Trey Grainger.